Salam sejahtera and good day, sir. I'm Ong Hong Kai and my metric number is 286142. Now I would like to introduce our group to sir. My group consists of 3 persons, which are Khong Jun with metric number 286405 and Yap Jia Jun with metric number 287652. Today, we would like to present our group assignment 2 to sir. Now, let me begin our presentation with univariate non-graphical analysis for data of water level. First, we calculated the mean. In our Excel file, the water level data is located at column B and is starting at row number 12. We use the function equals mean in bracket B12 to B3328 to calculate the minimum value of the water level. After applying the function, we can see that the minimum value of the water level is 26.810 meter. Next, we calculated the max. Same for maximum value. We use the same data at column B and is starting at row 12. We use the function max in bracket B12 to B3328 to calculate the maximum value of the water level. After applying the function, we can see that the maximum value of the water level is 29.995 meter. After we get the value for min and max, we can calculate the range. To calculate the range, we need to subtract the minimum value from the maximum value of the water level. As we know, the maximum value of the water level is 29.995 meter. We can calculate the range value by subtracting the minimum value, which is 26.810 from 29.995 meter. After applying the subtraction, L12 minus L11, we can get the range value of the water level is 3.185 meter. Next, we need to find the central tendency values and the spread values. To determine its central tendency, we need to calculate the mean, median, and mode of the reservoir water level variable. After applying the function average B12 to B3328, median B12 to B3328, and mode B12 to B3328, we can directly obtain the mean, median, and mode values for the water level variable. The mean, median, mode values are 28.566 meter, 28.725 meter, and 28.975 meter respectively. To measure its spread, we need to calculate the variance and standard deviation of the reservoir water level variable. After applying the functions var b in bracket b12 to b3328 and stdev.p b12 to b3328, we can directly obtain the variance and standard deviation values for the water level variable. The variance and standard deviation values are 0.322 meter square and 0.567 meter respectively. Next, we use the function SKEW B12 to B3328 to calculate the skewness value of the water level. After applying the function, we can directly obtain the skewness value for the water level variable. The skewness value is negative 0.849424147. We use the function KURT B12 to B3328 to calculate the kurtosis value of the water level. After applying the functions, we can directly obtain the kurtosis value for the water level variable. The kurtosis value is 0.067898837. Now, I would like to summarize the analysis results for water level data. The minimum value of 26.810 indicates the lower recorded water level in the Timah Taso Dam reservoir during the analyzed period. The maximum value of 29.995 represents the highest recorded water level in the reservoir. The range of 3.185 indicates the difference between the minimum and maximum values, showing the overall variability of the water level. For Central Tennessee, the mean of 28.566 represents the average water level in the reservoir during the analyzed period. The median value of 28.725 represents the middle point of the dataset when arranged in ascending order. The mode of 28.975 indicates the most frequently occurring water level value in the dataset. The variance of 0.322 measures the spread of the water level values around the mean, indicating the variability within the dataset. The standard deviation of 0.567 quantifies the average amount by which individual water level measurements deviate from the mean. The negative skewness value of negative 0.849 indicates the distribution of the water level data is slightly left skewed, with a longer tail on the left side. The Curtis value of 0.067 suggests that the distribution of the water level data is relatively close to a normal distribution with less extreme outliers. Next, I will pass to my group member, Khong Jun, to continue our presentation.
Good morning everyone. Today I'm going to present the univariate non-graphical analysis for the data of rainfall. To identify the minimum value of the rainfall, we will apply the mean function of the Excel and select the rainfall data in the dataset. After that, we can see the minimum value of rainfall is 0. Second, we will identify the maximum value of the rainfall. To do this, we will apply the function in the Excel, which is max function, and select the data of rainfall in the dataset. After that, we can see the maximum value of rainfall is 643 millimeter. After that, we will find the range of the data in the dataset. To do this, we will apply the subtraction of maximum value and minimum value. After that, we will get the range value of the rainfall is 643 millimeters. After that, to identify the central tendency, we have to find the three components, which is mean, median, and mode value. To do this, we will apply the average, median, and mode function in the Excel and select the data of rainfall in the dataset, so that we can directly obtain the mean, median, and mode value for the rainfall variables. The mean of the rainfall is 26 millimeters, the median is 9 millimeters, and the mode is 0 millimeters. After that, to find the spread, we need to identify the two components of the spread, which is the variance and standard deviation. To do this, we will apply the VIR and STIS3033 function of the Excel and select the data of the rainfall. After that, we will directly obtain the variance and standard deviation value for the rainfall variables. The variance of the rainfall is 2,215 millimeters, and standard deviation of the rainfall is 46 millimeters. After that, to identify the skewness of the data for the rainfall variables, we can apply the skew function in the Excel and select all the data of the rainfall in the dataset. After that, we can directly obtain the skewness value, which is 4.23 for the rainfall variables. After that, to identify the kurtosis of data of the rainfall variables, we can apply the crew function in the Excel and select all the data of the rainfall. After that, we can directly obtain the kurtosis variable, which 29.636 for the rainfall variables. So now I explain about the inference for the data of the rainfall variable analysis. The first is the minimum value of 0 indicate the instances when there was no recorded rainfall at the 5 gauging station during the analysis period. Second is the maximum value of the data for the rainfall variable. The maximum value of 643 represents the highest recorded cumulative rainfall during the analysis period. The next is the range of the data in the rainfall variables. The range of 643 shows the differences between the minimum and maximum value indicate the overall variability in the cumulative rainfall. The next is the central tendency. The central tendency have three components which is mean, median, and mode. The first is the mean of 226.2 represent the average cumulative rainfall record from the 5 gauging station. The median value of 9 represents the median point of the datasets when arranged in ascending order. So the last is the mode of 0 value indicate the most frequently occurring sin categorical when there was no recorded rainfall. So the next is spread, which has two components, which is the variance and standard deviation. The first is the variance. The variance of 2,215 quantify the spread of the cumulative rainfall value around the mean, indicate the variability within the dataset. The next is the standard deviation. The standard deviation of 47 measure the average amount by which individual cumulatively rainfall measurement derived from the mean. The next is the skewness of the rainfall variables. The positive skewness of value of 4.23 suggests the distribution of cumulative rainfall data is highly right-skewed with a long tail on the right side. This indicates the few of instances of very high cumulative rainfall value compared to low level value. And finally, the kurtosis value of 29.63 indicate the higher degree of pickedness and heavy tail in the distribution. This suggests the significant outlier or extremely value in the cumulative rainfall data, potentially indicating period of intenser rainfall event.
Good morning to everyone. My name is Yap Jia Jun and my metric number is 287652. So I'm going to explain about a univariate graphical analysis, and this is the histogram for reservoir water level between 1998 to 2007. So for the x-axis, we use flood state, which are normal state, alert state, warning state, and danger state. And for the y-axis, we use frequency. The majority of the recorded water level data falls within the normal stage, as evidenced by the highest count of 2,493. The alert stage has a relatively lower count of 781, indicating instances when the water level is slightly higher and closer to the warning threshold. The counts decreased significantly for the warning stage, with only 31 occurrences, indicating infrequent instances of water levels nearing the warning threshold. The danger stage has the lowest count of 12, indicating rare occurrences when the water level exceeds the warning threshold, posing a significant risk. So the next one is the histogram for rainfall between 1998 to 2007. And for the x-axis, we use categorical data, which are non-rainfall, light, moderate, heavy, and very heavy rainfall. And for the y-axis, we use frequency as well. The highest count in the rainfall data is for the non-category with 1,079 occurrences, indicating instances when no rainfall was recorded. The light and very heavy categories have similar counts with 718 and 436 occurrences respectively, indicating that both light and very heavy rainfall events are relatively common. The moderate and heavy rainfall categories have similar counts as well, with 674 and 410 occurrences respectively, suggesting that moderate and heavy rainfall events occur less frequently than light and very heavy rainfall. As for the inference, the histogram analysis of the water level data reveals several important inferences. Firstly, the majority of the recorded water level data falls within the normal stage with a count of 2,493. This suggests that the water level in the Timataso Dam reservoir typically remains within a safe and acceptable range. The high count in the normal stage indicates that the reservoir operates within its intended capacity for most of the time. Additionally, the counts for the alert, warning, and danger stages gradually decrease, indicating less frequent occurrences of higher level water levels. This suggests that instances when the water level approaches or exceeds certain thresholds are relatively rare. The relatively low counts in the warning and danger stages, which are 31 and 12 respectively, indicate that reservoir experiences only occasional situations where the water level poses a potential risk or danger. Overall, these findings indicate that the Timataso Dam reservoir maintains a stable water level within a safe limits for a significant portion of the analyzed period. The histogram analysis of the rainfall data provides insights into the frequency and intensity of rainfall events around the Timataso Dam reservoir. Firstly, the category with the highest count is none, indicating instances when no rainfall was recorded. This suggests that periods of no rainfall are relatively common in the region surrounding in the reservoir, which may have implications for water resource management and overall reservoir capacity. The counts for the different rainfall categories indicate the occurrence of varying intensities of rainfall. The light and very heavy categories have similar counts, suggesting that both light and very heavy rainfall events are relatively frequent. This implies that the region experiences a mix of moderate rain showers and occasional heavy downpours, which can contribute to fluctuations in the reservoir water level. On the other hand, the accounts for the moderate and heavy rainfall categories are lower compared to the light and very heavy categories. This suggests that moderate and heavy rainfall events occur less frequently but can still have a notable impact on the reservoir's water level. These findings highlight the importance of monitoring and managing the reservoir's water level during periods of moderate to heavy rainfall to ensure its safety and stability. In conclusion, the histogram analysis of the water level and rainfall data provides valuable insights into the patterns and characteristics of the Timataso Dam reservoir. The majority of the water level data falls within the normal stage, indicating a generally safe operating state range. The rainfall data shows variations in intensity, with instances of no rainfall, light showers, and occasional heavy downpours. Understanding these patterns can aid in reservoir management, flood control, and water resource planning in the region. And that's all for our group. Thank you.